Welcome all you tech enthusiasts, you curious minds, and those navigating the electrifying world of bits and bytes. This is 𝐀𝐻𝐸, the podcast that promises to be your guide through this ever-evolving universe of IT and beyond. So, let's do it. Hi everyone, my name is Adrian, and today we're talking about robotics. And today I have with me some amazing experts from SoftServe that would shine some light on this topic. I have Mariusz and I have Jakub. Hi guys, how are you?
Hello, I'm fine.
I'm fine too, thank you.
Good guys. I hope you will kind of explain to us and to me a bit more about robotics, but first let's start with some introductions, if that's okay. Yeah?
Sure.
Mariusz, how about you? Let's start.
Okay, so I'm Mariusz Janiak. I'm a solution architect here at SoftServe. I work here more than 3 years already.
Okay.
I'm leading the smaller team inside the robotics team, which deals with mathematical modeling, numerical simulation, control and optimization. And I'm passionate in robotics. It's my background. I study robotics and control at the university, and then also spend some time a little bit more there to investigate this topic deeply.
And how long have you worked with robotics in general?
It's a good question. I would say 15 years already.
Okay, so it's safe to say you know what you're talking about then?
I wouldn't say so. It's, I don't want to present myself as an expert because it's easy to be an expert, but I would say that I have some hands-on experience.
Okay, perfect.
That I prove in industry, also in academia.
Okay, good. We'll dig into that a bit later then.
Sure.
Thank you. Jakub, how about you?
So, I'm senior robotics engineer here at SoftServe, and I work here for almost 3 years. In general, I have similar background as Mariusz, let's say, but not for so long. So I also work with different kind of simulations, digital twins, but we also control different kind of robots.
Okay.
Last year I also started a PhD, so I try to get additional knowledge also about outside SoftServe. Yeah.
Okay. Perfect. Thank you. And I'm assuming that, studying a PhD and working in the same field helps you a lot?
Yes, I think. Yeah.
Okay. Where did you study? Where did you do the PhD?
At the Wrocław University of Science and Technology.
Nice. Hello to everyone from that university.
Yeah.
Okay, good. Quick question before we get on with the set of questions I have for you. Cats or dogs?
Dogs.
Okay, good. That was a consternation there for a second.
I mean, it took me a while to understand the question. Yeah.
Oh yeah, sure. Okay. I was very kind of intuitive. Yes. Do you prefer cats or dogs?
It was unexpected.
Good. Well, I'll try to keep those two a minimum.
What about you?
Oh, dog. Since I was little. Yeah, love dogs. Now I have one Irish setter, 4-year-old. So yeah.
I have two.
You have two?
Dogs.
Two dogs. Nice. You see, at least they have something to do together. Nice. Good. Jakub, do you have any dogs?
Yes. I have one.
Perfect.
From shelter.
See, now I really like this episode. From shelter as well.
Yes.
That's really good. Really good. Yeah.
So here we agree. Let's see.
Yes.
So far, so good.
So far, so good. Believe me, I had episodes where there was some conflicts there. Somebody preferred turtles, for example. So it's not that obvious, you would say. Okay, perfect. All right, guys, let's get to the merit of this episode, and it's robotics, right? But let's maybe start from a high level. What is robotics? For somebody who's not technical enough, can you shine some light on this whole kind of industry or this area of Center of Excellence?
Jakub, please start.
Jakub, yeah, in general.
Yeah, it's so general question, so it's hard to even answer. But in general, if we talk about robotics, we call about all the intelligent machines. I would say, but maybe not as like the PLC machines that we can see in a warehouse, but more like robotic arms even Roomba in your home is considered as a robot. So
perfect.
If we talk about robotics, it should be in general intelligent and autonomous, but it's not always the case.
Good. No, I appreciate this high level overview. And this was a bit of a curveball as well, question. But simply I asked it because robotics is such a vague term for those who are not that technical, right? So like, I like how you used the example of Roomba, right? Not everyone, but a lot of people have those at their homes. So that kind of brings this topic a bit to the ground level, right? Good. But what does modeling and simulation actually involve? Because this is what your speciality is, right?
Before I will answer this question, I would like to also add 2 cents to
go for
robotics, general robotics, because it's hard to draw the line between the automation and the robotics, right? There is always a discussion, where is this line? Generally, we think of like automation and control as machines that can act independently without the human intervention, right? That some processes are automated, so we don't need to, do the manual work. And then I think that the robotics evolved from this concept of the automatic processes, machines that do some process, but we add some additional things there, like that they can. They have some features, like they have locomotion, so they can move around, can move object around, and they can travel from one point to another, and they have some agency, let's say, that they can make decision depending on the context, what they see, what is going on in the environment. So this put additional challenges for the designers of the robotic systems, because right now we need to start acting like the humans, right? You need to be able to perceive the environment, understand what is going on, and then make decision how to proceed, right, to achieve some goals. And those goals are a little bit more high level defined than when we have an automatic process. All the goals are clearly defined, nothing change in the environment. We have like fixed conditions, but in robotics we are like shifting in the direction that the environment is variable. Everything may change and we need to adapt, right? And this adaptation is like component in robotics that I think is not present in automatic control. It's not always the case right now, because this right now automation also try to like be able to adapt to certain conditions, like weather, for example, change, something happen, right? But generally, I would make this distinction in this way.
Okay, perfect.
I think that it's also worth to add that you said about the border between automation and robotics, and I think that robotics is mostly inspired by nature. So it's not a case of automation, but in robotics. Even in case of construction, maybe Roomba here is not a good example, but all the robotics arm, the robot dogs and the humanoids robots, and all the perception that we do. So the computer vision, we use cameras there and so on. So they try to be similar to like animals and people rather than
so
humanoids.
In this sense, we try to like recreate the capabilities that humans and animals
have. And we often inspired by nature.
Yeah. No. I mean, when you first hear robotics, you think of iRobot movie with Will Smith, for example, right? All those kind of, when I think about it, I think about those arms, like you mentioned, from ABB company. They're quite famous in robotic space as well.
Star Wars. The first.
Yeah, that's true. No, I'm a big fan of iRobot. That's why I keep bringing this up. Star Wars, that's true. You're absolutely right. But that goes kind of in the sphere of fantasy there. All right. Okay, perfect. Good. Anything to add about simulations and prototyping? What does that involve? Have we covered this?
We haven't touched the topic yet, so let's try. explain what is going on.
What does it involve? Or what is it?
So in SoftServe, but also this is also a trend in industry, we have something we call simulation first approach. It means that before we build, we start first in simulation. So instead of building the prototype, right, physical prototype, we tried our ideas in simulation first. So it means that we need to have some kind of representation or models of the robots, components, environment that allows us for building this concept there and testing in simulation. So this is where the modeling comes into the play. We need to describe how some things behave, right? We use this mathematical, for this we use mathematical formulas. And generally, modeling is about how to describe using math the behavior of some objects in real life.
Machine learning.
Machine learning is one way how you can achieve that. We call it black box approach, that we don't know how some things work, but we have a lot of data, so we can try to build the black box model that based on the input-output relation describe the behavior, right? So we can kind of discover this from data. But we have like standard approach, like we call it first principle approach, where we know, for example, Newton law, right, or some more advanced math. Then we can use physics. We use physics, physical theory here to describe the behavior of the object, and this is like very good description because we prove, right, through the years of science that it works, right.
Yeah, it makes sense, and it drives the cost down because you don't build those physical machines or robots. You first test them in their environment.
Yeah, exactly.
Nice. Jakub, anything to add to this topic?
I think that it's worth to add that what is modeling in general. So at some moment, I was a little bit shocked that we can describe different objects around us, and for example, also more complex devices like car using math. So if we talk about modeling, you can think of it like a function. So like standard linear function y equal to ax plus b that gets some input and produce some output. And this is a simple example, but for now you can just assume and that you can describe most of the objects and physics around you using math. So then you can test how it will perform, how it will works for different inputs, trajectories, and so on. And it's about simulation, yes, later on.
Okay, perfect. Thank you.
Yeah, but because of we use math, it's really, let's say, easy to analyze, because these days we often talk about machine learning and AI, and in this case, we put everything into a black box, and we are not sure what happened inside. So
So maybe let's also introduce these concepts, right? We mentioned the black box approach when we don't know how the things works, but we have a lot of data and we can discover how they works through machine learning, for example. And we have this white box approach when we know how the things works, and we can describe with equation how stuff behave, right? And this is approach which we use when we don't have a data, and we need to generate this data. And this is also the concept of synthetic data generation. I mean, maybe we will touch this topic later, but this is also part of the modeling and simulation to deliver the data for machine learning or AI agents to train them in simulation, right? I don't want to go too much into
technicalities. We will need a whiteboard.
Yeah, exactly. So we have also mixed approach, right? If we have white and blacks, there is also some
the gray area.
Gray area, exactly. And I think this is the most interesting approach right now, and this is something what we also trying to learn how to do it properly in my team in SoftServe. How to combine the goodies from both worlds. Like if I know something and I have some data, let's try to maximize the effects, right? Combining those two techniques. Sometimes it's easy to describe, like, for example, motion of the car, right? We know the Newton laws, okay, cool. But there are some disturbances, like, I don't know, wind or whatever, temperature. And we don't know how to exactly it influence at certain time the behavior of the system. So then we use this machine learning to discover those missing components.
Yeah, there seems a lot of factors. Yeah, like it's maybe not that obvious to somebody, but there's so many factors to take into account when actually working on simulations. Like you said, wind resistance or surface or pressure, tire pressure, for example, of a car, right? Yeah. So you have to take all of that into account.
When we discuss the modeling and simulation, there is something we call the fidelity of the models. And we need to be aware that we can't have the perfect match between the reality and the models. Models are always approximate the reality, right? So we can be close, but never,
Sure.
And depending how close we need to be, we need to put much more effort to get like closer and closer. There is this Pareto effect, for example, that it's easy to achieve this 80%, but to get another 20, you need to put much more effort to get there.
Yeah, that makes sense. Okay, well, thank you. Guys, let's maybe move on because Jakub, you in your introduction mentioned digital twins, and I just want to cover this for a second. How are digital twins used in robotics? And I've heard this before, they are quite powerful. So why are they so powerful and important?
So in general, if we talk about digital twins, they are like maybe extension of simulation. So they are different types of digital twins. The basic one is monitoring. So you can think of it like 3D representation in simulation of our robot or some more complex system. So then the operator can just see in real time what happened with this device.
This is like the SCADA system. If everyone who is listening is familiar with the industrial concept, the SCADA is the kind of monitoring twin. When you have the visualization of the processes, you have data that feeds the system, and you can see what is going on your production line, for example.
Yeah, exactly. So you can think of it like a robotic arm in real world, and each joint has encoder, so we can get the position of the joint and we can visualize it in the simulation. So it's just 3D representation in simulation of our robot. But then we can get the historical data and make some analysis.
Okay.
So then it's a next step. Next, we can have the modeling of the robot, and we can use it to predict some behavior.
So you can
using
test
the
what if
digital
scenarios,
twins.
for example.
Yes,
It
yes.
seems
What
like
happen
a
if
testing environment.
So the basic digital twin cannot predict. It can just like observe the real object. But when we talk about the predicting digital twins, we can test different scenario and see what happened. Yes, if we will apply the same control to the real robot or real system. Then next step is to put some warning to the user. So if we can predict the future, yes, using the model, and our real object is in some dangerous situation, we know that there is a high probability that something wrong may happen, and we can pop up some warning and but without taking actions.
Okay.
And taking autonomous action is a next step of digital twins. So it can, for example, in some simple scenarios, just stop the system, yes, before it will fail, before it will crash, collide with something. And I think it's the final, yes, adopting digital twin.
I mean, we are closing the loop. This is also some kind of concept of control theory. But in digital twin, it means that we are able, on the low level, like Jakub said, collect the data. Then we have the methods to analyze this data and make some kind of prediction, assumption about what is going on. Having the data, we can start building the models and verify those models, the accuracy of those models. So in the simulation, we can make some decision, right? We can check our ideas, we can tune the parameters, then we can make some decisions. So apply the new control based on our findings, right, to the system. Then we are collecting data again, do this prediction, updating the models if models were not valid, so we can improve the model, run the simulation, check find the better control, apply, and close the loop in this sense. So this is like autonomous systems that not control the one element, but it can control the whole factory, for example, or the whole your business without the human intervention.
Yeah, it seems like a continuous improvement principle as well. And again, it also seems like something that's a necessity rather than optional, but I don't know if I'm right, but not every machine has its digital twin, right? Okay, so it's just whenever you choose to apply a digital twin, then you have that and you can control this environment, simulations, and collect data. But should it be best practice then to have it? Or is it expensive to have a digital twin?
Before I will answer this question, we need to also mention that there is no consensus what exactly digital twin is in the, let's say, scientific society, right? Everyone has its own definition. It's not good. Okay. So depending where you check, right, whom you ask, you get different answers. Very often by digital twin, they means just the simulation that you have models that you can simulate, right? In SoftServe, we think about the digital twin in a little bit broader sense. So we define those levels of maturity, but the final goal is to have this autonomous twin which has this closed loop features, right? Getting back to the question, if this is a good idea, I think this is the future. This is where the industry is going right now. So we are collaborating with various vendors, also the vendors who produce the machines for producing the financial goods, like goods that other buy to produce some other things, right? And the request is that if I'm like, for example, I'm building the car and I need to have a factory line, right? So each component of this factory line should have its own digital twin. I mean, the vendor who delivered this piece of the factory line should provide a digital twin that when I build the whole factory line, then I can connect all those twins together and have like metaverse, we call it.
Virtual
industrial metaverse.
Factory,
Yeah. So you have,
line.
And those like OEMs, we call them OEMs, they don't want to build those digital twins from scratch. They ask the vendors to provide the components to deliver the digital twin of this particular component. There is no standard, and I think we are on the way to define it. Okay. And we have some influence also as a SoftServe for this process.
Yeah, so in essence, everyone can deliver a different type of digital twin that wouldn't match or be combined.
This is the problem. If there is no standard, okay, I have whatever we name it, hey, I have digital twin, right? But how I can use it, right? What it brings to the table for me, right?
Makes sense. Okay, all right. Well, thank you. Yeah, digital twin seems, again, necessity for me, but I understand it's more complex than that. Good. I want to ask you about the life cycle of prototyping. We've touched on a few steps, but can you walk us through what does robotics prototyping life cycle look like?
It depends, I would say. Yeah, but first we need to know the requirements. So generally, if we want to, let's limit to some robotics application. Yes, let's think about some robot, for example, robotic arm or mobile robot. So we need to know what are the future tasks of this robot. Yes, and what are the requirements in sense of, for example, how fast it needs to move, what payload it needs to carry on, and so on.
We call it like functional and non-functional requirements, right? There are some specific things that are important to solve the problem, like we call this functional, and some that are not super important, like the color of the robotic arm, for example.
Sure.
Right? So that doesn't influence the solution of the problem, but has impact on other things.
Aesthetics.
Not only, I mean, this is not only aesthetics, but other things that are not take part in solving specific problem, but are important for the customer for some reason.
Okay, so you first start with the problem, and then you move on to prototype.
And this phase, I think, is crucial and really important because if we make some assumption at the beginning and we will manufacture this prototype, design a control system, all the interfaces and so on, and at the end someone will, ask to change those tasks of this robot and the requirements, it would be really difficult and it will influence the costs. So it will be not 1 week change, but it can be.
Sorry, I don't want to interrupt.
Yeah. Sure.
I mean, also it depends. This like life cycle or the project approach depends on the business or industry. Let's say we have a little bit different standard in industry, a little bit different in academia. So probably if you will ask how it works in academia, it works a little bit different. So and it was also there have been a different approach for like project management. Like there's very popular V cycle in industry, especially in German industry, for example. But there are different approaches for building any new solutions. So yeah, like Jakub said, we need to have these requirements first. We need to understand what we are building, what is the environment, where it will be operates, what are the conditions, what is the performance criteria, what are the KPIs, right? How we will measure the success, right? And so on and so forth. So a lot of stuff that we need to find out. And we call this discovery phase, like we try to discover this first. And then, I mean, depending on the team and the approach, we have kind of ideation phase where we try to come up with solutions. And this is typical like research and development, I would say. Like we represent the robotics team, which is part of the CE Center of Excellence. And for me, this part of the SoftServe is like research and development.
Well, it certainly is. You're doing things that are not typical standard. You're developing something that's potentially new and complex that not every kind of client of ours is looking for. This is a very specific area of technology, right? Yeah,
we delivering the custom solutions, right? So there are probably better or off-the-shelf solution on the market. If this is fits the client's need, just use it, right?
Yeah.
But if you need something custom, this is where we come into the play and help you with solving problems.
Yeah, makes sense. And then just from my understanding, the life cycle can be obviously varied depending on the solution itself, but it seems that the first stage, which is discovery, is the most important of all, right? To understand the problem, to then design the solution. It's kind of like design thinking concept.
Exactly, yeah.
Yeah, so
this is what we're applying,
to yourself. Perfect. I recorded the episode on design thinking.
Cool.
So that's why. Okay, good. And it makes sense, right? So you don't spend and waste time on developing something that at the end will not actually fit for purpose, right? Good. Anything else?
Yeah, I would like to add something. I think that it's quite interesting and important that even if we have all those requirements, so for example, if we think about robotic arm, we know that it should, carry on 5 kilograms and so on. So what we should not do, we should not purchase the hardware. And this is, I think, the common mistake in small companies, in startups, that they want to create some prototype as fast as they can to show it, on some conference. And
hey, we have solution, right?
Yeah.
It took 2 months and it works, right?
Yeah, exactly. So what we should do, we should then create a simplified CAD model of this prototype and perform simulation and make sure that it will be able to perform certain tasks. And then start purchasing hardware. Because during the simulation, we can find out that it may just not work. And if we start from hardware, we will need, spend a lot.
Yeah, I was working in my previous job, I worked for a startup. And they skip this simulation, prototyping in simulation phase. And we had a lot of hardware prototypes, which cost, I don't know, a lot, right?
I can imagine.
And we lost a lot of time, effort to improve it. The cycles, development cycles were longer, and the results were, I don't know, not satisfactory, right? Because we had number of cycles. So from my perspective, it's much better to start with simulation. I mean, even building the models is also the effort. It's not like for free, right? Sometimes it takes as much time and effort to build the model, like building the hardware equivalent. But in simulation, it's much easier to experiment. You can change every component. It doesn't cost you anything. If you have this model, right? Yeah. You just change the parameters, like length, mass, whatever you need to change there. You have access. You can do it. I don't know. Easily you can run bunch of experiments, right? This is just a question about the hardware resources you have, right? How many PCs or cloud resources you can involve.
Yeah, it just seems like you want to build a POC just to show off potential capabilities without understanding or knowing if that capability is even feasible.
Exactly.
Yeah.
Yeah, but I think that the main problem why companies and people skip this part is that it's not spectacular. When people see simulation, it's nothing spectacular because it's for non-technical people. It's really difficult
like animation, right?
To distinguish.
Everyone can do it, right?
If you will show a physical simulation of a robot, some people can think that it was in these days AI generated or it was animated, that there is no physics behind it and so on. So it's nothing spectacular. But if they see a real device that moves, that performs some task, they are impressed. And I think that it's the main problem.
I get that. But it kind of seems like it all depends on the maturity of your client and understanding the actual concept they want to develop. I mean, I agree. If I also see a mechanical arm on this desk, I'll be impressed, right?
Yeah,
and it makes sense, but it just doesn't make sense to buy something without knowing if it works, or to spend money developing something that
exactly.
Yeah, so I guess more education towards our clients or clients, vendors altogether to understand that first you need to simulate.
I don't want to complain on our clients because they are,
Not that, but they are clients because they are doing the right thing.
But what I can say recently, the clients of SoftServe, they are quite aware what is going on. That the simulation makes sense and this save a lot of money, right?
Yeah, and it says a lot about their maturity as well.
Still, there is some room for improvement in terms of digital twins, like applications, because there is a hype on the market right now for that. I can say that a lot of companies would like to have a digital twin, but there is always the question who will use it and why you need it, why you supposed to invest a lot of money and for the toy, right? Mm-hmm. So if there is no business case, good understanding, we are not advising to go in this direction right now.
Okay, so that's good. That says a lot as well. That we're not pushing solutions that are not necessary. Yeah. Good. Thank you, guys. Okay, I want to switch to the topic I want to talk about because we kind of again touched on it previously with the car example, right? Mm-hmm. Because simulating real world complexities must be quite difficult. Like how do we actually replicate those complexities, which again probably involve a lot of physics? How does that work?
Jakub, maybe you can start. You are like specializing right now in your PhD on this topic, so.
Oh, there you go.
So generally, it's
go high level without details.
I'm thinking
we'll grade you at the end.
How to touch this topic without going into details. But generally, we start at the beginning talking about the mathematical representation of the robot. So we have some common equation to describe some standard behaviors. Yes, they are equation for describing the movement of the car. But then, if we talk, for example, about the friction of the wheel, so the friction between the wheel and the ground, the terrain, it's getting more complex, especially because the car can drive on different terrains, So for this, we also have equation, but the problem is that it can change depending on the environment, and it can change over time.
Yeah, if it's moist or if it's dry outside.
Yeah, I'm sorry that I'm jumping in here. I remember when I started studying the robotics at the university and professor came and say, hey, today we'll have a robotics theory. Everyone have been excited. Okay, cool, right? And what the professor said, assume that the robot is described by this differential equation. And after he said it, it was the first sentence he said, right? We haven't seen a robot at all. We only discussed this equation. So all the robotics lectures was about math and how to, do something with this equation, how to properly describe things. And the robot was only like the, I don't know,
imagination
starting point for the discussion, right?
so he bought your interest. By mentioning robots.
So anyone who going to study robotics, you need to be aware that sooner or later it will involve a lot of math, like calculus, algebra, stuff like that.
It seems that way. Yeah, definitely. But at some point you will see a robot. At some point.
At some point, yes. Later you go through all those basic math, let's say, right? Then you get the hands-on experience with the hardware. You will build your own robot, right?
Yeah, makes sense. Okay, sorry, Jakub, you want to continue?
I stop on the friction. So the basic movement of the car we can describe using the equations, yes.
Rigid body dynamics. We call it
rigid body dynamics. And there is no parameters that can change. And usually, for example, in case of car, we have some dimension of this car, like wheel diameter.
Let's explain what the rigid body dynamic means. What it describes. Motion of the rigid body. And there are also some relation between rigid bodies. Sometimes there are some constraints. So we also describe this relation. And it describes how forces impact the motion of this rigid body. So this is a relation between external forces and the motion, like position, velocities, and accelerations. Okay. So this is what we mean by rigid body. So we always have some forces on the input. And this is like forces that come from the engine, for example, right? From the ground, from the wind, I don't know, whatever forces act on the object. So this is what the rigid body dynamics means.
Thank you.
Yes, and I wanted to say that let's say that this is the easiest part, because then we have some more complex stuff like friction. Let's talk about this car.
Force component, like on the car.
And here we have a problems because we have the equation, but there are some parameters, and how to get these parameters. So then we need to get the data from the real.
Every equation has parameters. Like when we discuss the models, we talking about parametric models. So it means that we have this like magic formulas, and there are some parameters like the mass, length, I don't know, radius, whatever, right? Some coefficients like
to tweak those parameters.
Friction coefficient, for example, right? And sometimes we need to find out those coefficients. We don't know exact value of those coefficients, but they influence the behavior, right?
So some of them we can directly measure, like dimension of the robot, like wheel diameter and so on. The mass, but the friction coefficient is not obvious how to get it. And then we need to get the data and do a
We need to set up an experiment.
Yes, exactly. And we need to do something which is called model identification. So it's another concept. It's about finding all the parameters from those experiments.
Is there a lot of guessing in that? Or what's the kind of... Because again, I can understand the complexities there, and to measure all of those parameters.
I mean, I would say that first we apply the knowledge we have, right? So, in the sense, it's just knowledge, but you get to a certain point that you need to use your intuitions, right? Because there are some things that you are not sure how they work, or what is the proper description, and you use this intuition. So this guessing, there is at some certain point is involved.
Yeah, but at the same time, if we talk about automotive, like the example you gave, Jakub, right? It's been going on for so long. I bet there's some sort of repository with the parameters on friction and all of those. Is there like commonly open source used repositories of those data inputs, for example? Or do you have to kind of measure it and design it or develop it yourself from scratch?
I mean, they are some parameters of certain materials that we use, for example, in the tire, yes?
Yeah, you have a tire, you have a tarmac.
So, yes, this can be the initial guess. But, the shape also affect this friction later.
Humidity.
Also, Also, if we talk about a friction, it's, between two different objects. So it also depends on the terrain, on the surface. And then we need to collect some data sooner or later. And this is still, let's say, not that difficult case. So we talk about the parameters that we can directly measure. Then we talk about the parameters that it's, hard to maybe measure directly or guess, but we still can perform experiments. But the most difficult case is when the parameters change over time. So you can imagine, for example, that the car is entering a different surface, or the parameters, the friction just change over the time because
or just weather change.
Yes, or just weather change.
We have rain right now.
We have rain.
Sunny day, right?
Yeah. So if you want autonomous car, we should have the learning. So we should adapt to changing environments, and it should collect measurements, process them, and updates our model.
But humans can do it, right? We know how to adapt, right? We learn along our lives how to do it.
Put the code,
And this is what we try to put into the robots right now as well, right? This capabilities to adapt properly, right?
Okay, good luck with your PhD, by the way. Jesus. Okay, now that sounds fascinating, to be honest. Because
I have one more thing to add. Because very often what we facing in our work is that we have those models. We even have those parameters you ask, that is there something, right, off the shelf. Yeah, and we write those equations. We are happy, right? We run an experiment to check, how good our model is. And we find out it sucks. And what's then? Everything is on the paper perfect. Like, we get all the things, all our knowledge is there, right? And it's still not good enough. And this is the problem we have, right? That there are some components that we didn't capture, or we don't understand, or someone didn't tell us that this is the case. We had such project, by the way, that we find out along the way, when we were in the identification process of some HVAC system, that there are some additional sources of energy that someone delivered a lot of energy to the system, and
you didn't anticipate those.
Didn't tell us about that. So we use standard method techniques. We build the model. Everything is fine, but in certain period of time, it was probably winter, I don't recall, the model changed, it doesn't work, it's not fitting well. And we, spend a lot of time to figure out why.
What
maybe
happened?
It's, we're doing something wrong. We did everything and ask, hey, at this time something happened, right? Yeah, we are putting some additional air from other part of the system. So sometimes it happens.
Root cause, yeah, definitely. Yeah, surprises happen everywhere in development phase as well.
But
that's true.
I mean, nice thing with the modeling, when you have those equations on the table, you understand what is going. You understand physics, right? And you can discover these disturbances that something is lying you, like math or knowledge or
a person.
Person, right? And you have a proof for that. On the paper.
Human errors happen often, I bet. Okay, good. Guys, let's maybe go into a bit more technicalities. And again, briefly, because maybe for our listeners as well as for myself, it would be good to understand what technology lies behind robotics, prototyping, and simulations. After all, it's all IT we're talking about. So what kind of technology tools do we use? In SoftServe, for example. Jakub, I can see you want to talk.
I wanted to start from my standard sentence, so it depends. If it's industry or if it's R&D or some prototype at academia. So in general, a few years ago, it was more common to use low-level programming language. So let's start from programming language, like C, C++. But now it's more common to use Python, especially for the prototyping and R&D. And why? Because it's much easier and faster to prototype with this language.
It's very versatile. Python.
Yes, it's versatile. It's also easier to learn. And so, if we have a C++ expert, then yes, maybe we can do the same within the same frame, but it's much more difficult to find a specialist these days on market from the low-level programming, and that will also know all the robotics concept, yes? So if someone is a C++ expert, usually this person limits to programming language, not to all other concepts around robotics. So it's just...
this heavy math, I mentioned the calculus, algebra, control theory, a lot of good stuff.
So we have the kind of educational part, which is, you need to know physics, mathematics, algebra, as you said, right? And then you have the coding principles or tools or platforms. So,
but coding is only the tool, right? This is like, hammer for doing stuff that are needed to be done.
So you can imagine that we have a good person after some academia that know the calculus, the algebra, the physics, and even robotics concepts. So then it's much easier to learn such a person Python than C++. And this is one reason, but it's also faster to prototype. We just need to write less code than in some low-level programming languages. And another thing, maybe not all, but most of the AI is written in Python. There is a lot of computer vision algorithms that also use Python, so it's versatile language. I
would say that the front end is in Python, but the backend,
but
the core of the computation is like low level.
Exactly. But that, let's say, typical data science engineer.
It would be Python.
Yeah, would be Python to just load the data to just
orchestrate the operation.
Exactly. So it's versatile language that we can use for different.
But not only programming language is important, because the question was about technologies.
Exactly.
Yeah.
So then we talk about all the simulation tools. Yes.
Yeah.
So at SoftServe we use quite a lot of NVIDIA tools. For example, NVIDIA Omniverse.
Isaac Sim, physics, physics, warp.
So there are some tools to visualize all the 3D assets, yes, but there are also different physics engines. So physics engines are responsible for all the rigid body dynamics. So if we have just a visualization and we put 3D objects there, it will not
it will be animation. I mean, if you want to see how they move, acting properly, interact, like when there's a collision or something happen, you apply some forces, right, to the objects, then this is the simulation.
Yeah, you need a lot of GPU power to help you with that.
We have some specialty, I would say, on the market in terms of Omniverse and high fidelity simulation. So we specialize something we call co-simulation. So we are able to combine different models and simulation engine in one simulation scenario. So one piece is the Omniverse with the physics, for example, for rigid body dynamics, but we can inject some external models from MATLAB, Modelica, ANSYS, whatever, and combine this and build really complex simulation inside Omniverse. And this is, we have our solutions, and we develop it and design it from scratch.
So if we talk about co-simulation, I think that it's really important to mention that there is a lot of different simulation tools. And why? Because there is no one tool that can simulate all the physical behavior.
Fits all the needs.
Yes, exactly. We have fluid dynamics, yes, for example. There are some special tools to simulate aircrafts, yes. Different to simulate
control system.
Yeah. navigation, perception, and so on. So using co-simulation, we can exchange data between different simulation tools and
synchronize the time between the models.
Yeah, so you apply the model or you apply the platform that's best suited for your need.
Yeah.
Because if something is doing everything, it's probably not that good. But if something is focusing on one area, it's probably good, right?
Sure.
So it's one of those concepts.
And even though we have, for example, 2 different simulation tools that can do the same work, because simulation can be used in a case when we have some specialists that know, one tool. This specialists don't need to switch to another tools. It can develop all the models within these tools, and we can use co-simulation to combine it together.
It's hard to force like engineer that has 20 years experience to, hey, I have super new tool for you. Just start using this one, right?
Yeah. Exactly.
I mean, on the market, it won't work, right? So this is why the co-simulation is handy here in this case. But there are a lot of other technologies we use in robotics. Very popular is ROS, Robot Operating System, which is the second, I would say, version right now, or second iteration of the ROS. So we broadly using this framework inside the SoftServe. And Jakub mentioned also the programming languages, but when we discuss the robotics system, we need to be aware that this is complex system, which is composed of different components. And we can layer those components. Like there is low level components which interact directly with the hardware, and typically there we use some low-level programming languages like C, C++, and recently Rust, for example. Sometimes we use also real-time operating systems to make it work in real time. And on top of that, we build the competency layer, which is the ROS probably play the crucial role when we have the navigation, perception, we have manipulation, and some decision-making algorithms. And on top of that, we have decision-making layer, it can be deliberative or it can be purely AI-driven when we have those agentic solutions, and then language, probably Python, I would say. But also when we use agentic approach, to be honest, programming language doesn't matter, right? Because they can generate the code
pretty much
in any language.
To what extent, what quality? Yes, that's true. That's true. We'll touch on that in a second. But okay, so just to kind of summarize, because it seems like first of all, you need to start with math and physics, and then you can kind of learn all the technologies. It's much harder to bring on a coder to teach him math and physics than other way around.
We had this exercise in our group that we thought, I mean, at a certain time we find out that it's hard to find the good experts on the market. So we thought that maybe it's a good idea to reskill the employees of SoftServe who are just good developers, and then we can invite them to robotics team. So we prepared the Skill Up program, which was 1.5 years of additional studying. And so far, there was no succeed with transitioning from development to robotics.
I can imagine it's just tough, right? It's difficult.
I mean, when you are a developer, you went through the university and you hear, hey, you need to study more, right?
Today again. Yeah, that's true. But it seems like an area, again, we're talking about center of excellence. We're talking about those kind of R&D spaces. You are looking for somebody who's passionate about this area. That's where you get the most value from, right? And then you will be successful in upskilling or reskilling. That's true. Okay, good. Guys, let's move on because you've mentioned this multiple times. I was holding my tongue to actually dig deeper. Yes, AI, because I'm a huge fan of AI, by the way, so I'll be a bit...
Elephant in the room.
Yes. And you know what? I mean, from all you are talking about, there's a lot of complexities in robotics. How does AI help? Can AI actually simplify a lot of things in robotics, taking into account it's not perfect, we have hallucinations, we have lots of challenges with AI, but does it actually help you at all?
Mariusz, I think.
Okay. So The question is not like straightforward.
Oh, no.
Generally, I would say, yes, it helped, right?
Okay, good. We're done.
Done. Okay. So robotics, or we were applying the AI in robotics for many years. Mm-hmm. So it's like not new concept there. But I would say we were applying this old type of AI, which was like mainly used for machine vision, like to perform some segmentation, object discovery and identification on the images. There were some other areas using for language processing, but the same way like we process the vision without this new generative AI approach. Mm-hmm. We were trying to use it for control, as a black box for modeling, right? So in these areas, it was performing well, but we didn't have this like agency capabilities that we can say that this is intelligent robot, right? And this latest findings in AI, the LLMs technology transformers, they introduced this concept of processing the natural language, and they proved they can do it efficiently. And this also brings the concept of agentic AI, that you can, by combining the different LLMs, you can build this reasoning system that can generally act like the human in the human environment, right? And so this also helped a lot to like think about the application in the areas where the traditional robotics were not applied yet because of this missing component, right? But if this like simplify our life, I wouldn't say so, because like training, like preparing these models to solve certain things is really challenging right now. And this is what we are like focusing. We try to learn how to use the technologies in the real life examples. Like, can I teach the robot how to move objects, like to generally pick and place, for example, tasks on the production line? Mm-hmm. And with the standard approach, it was like pick and place. We have robotic solution for that, right, on the production line. But doing the same with LLMs require like new training, and this is like ongoing things. Yeah,
to train the model to feed the necessary data.
Yeah, and you need a lot of data. And the thing is that the databases are not there yet, like good quality labeled data, which are needed for LLMs. So from this perspective, it's challenging. There is a promise, some
better tomorrow.
Yeah, better tomorrow. But I wouldn't say we are there yet. We are going toward this direction.
Okay, so in essence, it's not. I mean, it's helpful. It's useful to some degree, but it's not that massively present in robotics space.
You know that the thing is that these transformers, they processing the tokens, and tokens are kind of discrete. So you have like these pieces of the language that you can easily generate. This way we call it generative AI, right? That you can generate the answer using those tokens. The thing is that the physical world is not like language. We have some continuous process.
That's true.
It's hard to tokenize the physics. And this is where the lot of investment, also for example from NVIDIA, goes to, like how to train these new types of AI on the physical systems. We call it this physical AI, and this is why you need the simulation to generate those massive data, right?
True. And you think about it again from a non-technical perspective. If you have AI that has a knowledge of all the mathematical algorithms and all the physics principles, and you feed data of some texture or wind resistance, you would think that AI would be able to somehow simulate certain actions in robotics to help you with those prototyping or simulations. Again, maybe it's not as mature right now that will be applied, but
there are two things, like generating the equation. So AI can do it, I think, right now. So it has this knowledge. So you can ask, give me equation of the, wind, right?
Yeah.
Or rigid body dynamics. And you will get the math, the answer. But later, when you have this equation, you need to solve it. So you need to find specific solutions for specific input. And this doesn't involve this generative capabilities anymore. You need some numerical.
Is it because of lack of data then? Or because my next question, and I'll follow up, is about quantum computing. Will that fix it?
Okay, so this goes out of my area of expertise. So
let's stay in robotics.
So I can say, I don't know anything about it, so let's discuss, right?
Yes.
The thing is that with this equation, the thing is that to learn the physics, you will need to have infinite number of memory, because there is infinite number of solutions. There exists infinite number of solutions. So you can't learn everything.
No, naturally, yeah.
And this is the natural limitation of this new technology, that I don't think it will be able to learn at this way how we try to learn it, the physics properly. So this, because we need to know the solution, like how the system will go over time, right?
Yeah.
And you change one thing and it goes in different direction depending on the equation. So it's hard to learn every solution, right? Because it's infinite number. So quantum computing give you some
speed for processing.
Not promise, because you can explore all those capabilities in parallel. This is how I understand. Maybe let's discuss.
Okay, well,
what is your take on that?
I don't know. I don't know how quantum can help. I know that the capacity will be much greater than the typical PC. So maybe at some point it will help with speed up the process of analyzing huge amount of data and processing
possibly,
power.
Yes.
But whether this will be applicable, I don't know.
I don't know.
Yeah, but here we talk about some really specific goal, yes, about using AI to reproduce the physics behavior. And as I fully agree with Mariusz that these days it's a really challenging task. But anyway, AI is, I think, commonly used these days in robotics, like as Mariusz said, for like an assistant, yes, to generate the math equation. It's also commonly used in computer vision. And there are some specific tasks when computing the classical math equation, yes, it's just time consuming. And if we want to achieve real-time performance, it's just not possible. For example, we had one project when we have to compute fluid dynamics in real time, and it was not possible. So
to just give you a sense of what we are talking about, we need to solve the partial differential equations.
Okay. Nice.
On certain mesh, which is typically the grid is huge, and there is a lot of computation involved to solve it.
Yeah. Okay.
And it seems that there are some AI models that, let's say, are capable of doing that, but there are still some limitations. So you can imagine a water or a wind that hits some objects, and we want to generate the forces that acts on the object due to the flow.
The motion.
There are some turbulences, some vertexes. I mean, it's so complicated. And right now we have a project when we try to use AI for wind tunnel. There is a certain AI model called Domino that promised to be applicable in the wind tunnel application. Typically, you solve it using the computational fluid dynamics (CFD) solvers, which takes from hours to days to get the solution.
Results,
so this is how much time you need to invest into solving the one problem for one certain of parameters. So you change one thing and you start 2 days challenge again. So we try to find out the capabilities of this AI, and for now it seems that it's still not address the engineering requirements, like low error in the whole field.
Anticlimactic.
So it gives us the performance of computation, but lack of physics fidelity.
Yeah, you get the solution, I don't know, in seconds, right? So it's, come on, in terms of performance, it's huge. But at certain, because what you get as a solution is the field, like you have a velocity field, pressure field, whatever field. And at certain point in this field, the difference between the real solution and what you get from AI is like more than 100%. So it's just random.
Yeah. No, again, don't get me wrong, because this is actually good news, right? We would be in quite a difficult situation when robots would be making robots, right? Right now, you still need a human. The human part is still needed, so that's good. You know, at some point,
so
maybe
you opt for the human in the loop solution forever.
Yes. I mean, come on. We need to be, at some point, necessary to the whole life cycle.
Yeah, I think this is another good question, more like sociological or philosophical questions.
Yeah,
ethical, how we will earn money to be able to buy the goods produced by the robots, right? Because if we will be removed from the production, right, from the... So what we will do? How we will get money, right, for living?
Don't know. Maintaining those robots.
No, you said they will
maintain
by themselves. They will have
true.
Digital twins, autonomous twins, so they will improve constantly. And what then? Like, what we will do, right?
Yeah. Okay. I've talked about AI with multiple different guests about different topics, robotics, AI, and other human centric topics. And the conclusion is simple: we're not there yet. Like, it's fine. It's for the next decades. We're all good. At some point, maybe.
Still, we are good.
Yeah, we're good. Yes.
But it's crucial to know that generally, if we have some robot, for controlling the robot, the AI can outperform usually the classical control. But the main problem these days is ensuring safety. So because it's the black box, there are some work on that.
Good point. Another good point.
Yeah, there are some research, and it's more and more common to research the safety of AI. But it's still a big problem. So if we want to create some prototype just to show the capability, you can for sure find a lot of videos on YouTube. And these robots are driven purely by AI. Sometimes we use different models and we switch between them depending on the task. But generally the safety, if we want to use something in industry, the safety is crucial, yes?
I mean, there are no theoretical proof that this solution is safe. I mean, we can't prove using for example, you select certain AI technology, architecture, right? And you get the data for training and you perform specific training because you can shuffle this data in different way during the training. There is no proof that with this data and this technology you selected, you get the safe results. The answer for any input will give you the safe response of the system. So you always put some safety layer, traditional safety layer on top of it, at least in industry.
So when AI comes to robotics, it was common to use just AI and see how it will perform. But now what we see, it's more and more common to use the fusion of classical control with AI. So to use AI to get the performance that we are not able to get
traditional.
For example, by some optimization or some objective function. Those are some details, but generally we are not able to get there. But we should use the classical methods to ensure the safety. Yes. So this is what
that have a proof. There is a formal proof that this is how it works. We can write this on the paper and safe.
And it's safe.
We should answer the question if we should sit in a plane driven by AI.
Yeah, let's not go there. Let's get back to the Earth. And last question I want to ask you, because we're kind of running out of time, but just really purely coming back to need of humans in the whole process and how important the cross-disciplinary collaboration is in this whole robotics space. Tell me we are needed, and different disciplinaries are needed for robotics to succeed?
I mean, we were trying to say at the beginning what the robotics is, right?
It's complex.
It's always a trouble for me to answer who is the robotician, right? Who is this guy who do the robotics? And when you look at the robotics, generally, it mostly comes to the integration of different technologies. So depending on who you're asking, if he claims that he is a robotician, right, and what you are doing, he's doing like small component of the robotics. Like, for example, we are doing control or simulation. There is some guys who are doing for example, vision, some synthetic data generation, manipulation, navigation, and mobile control. Mechanics design, right? Some embedded stuff. Yeah. So robotics combine all those things, and we believe in SoftServe that there is no like full stack robotics developer. You can be specialized in certain domains. Yeah,
it's not that there is a robotics engineer, right? Or you can call him that way.
Yeah, we call it the robotics engineer, but you specialize in one of these areas, right?
There's a lot of kind of disciplines connected to each other too.
Yeah, we are like kind of integrator who understand all particularities, all other domains that are important.
Yeah.
And we know how to use it to build the autonomous machine to perform some specific tasks.
Yeah. So again, it's safe to say that this collaboration is crucial for the success of robotics projects.
I would say so, yeah.
Yeah, different components, different specialities in one.
Yeah, but I think it's more and more difficult to get that general knowledge from each domain. And it's more and more common that we have just a specialist from certain domain, like, for example, simulation, or navigation. And then we should have a strong lead that coordinate the work of the team.
Yeah, but even though this lead, who is really difficult to find on the market, he won't be a full stack that he has, experience and
technical knowledge. Yeah.
With all those specific stuff that are important for the technologies.
Well, he needs to fake it to make it.
Yeah, I mean, sure. I mean,
kidding.
But it's really hard because you need to spend the whole life to study some certain things, and you can't learn everything.
If you investigate other domains, you are not specialist in some of it. Yes, so you can either has knowledge from each domain or be specialist from one.
Yeah,
let's say.
Even in control theory, there is I'm, for example, expert. I'm not saying about me, but if someone say I'm an expert in control theory, but I will ask, okay, it's linear or non-linear? Is optimal or just some generic? Can you take into account the constraint or not? So, and when you ask those questions, those guys, when you find out soon that they specialize in certain area of certain theory.
Yeah, so you're not an expert. You're an intermediate. Makes sense. Good. Okay. Before I let you go, just to quickly, what's ahead for robotics? What can we expect from robotics in the sense of innovation? Anything new that will come up? We have AI now, as you said. It's not that
we have huge push for humanoid robots, right? I think right now on the market. So I think this is what we supposed to expect in the near future.
Are we close to that? A humanoid assistant at home who will make me coffee and prepare something?
I don't know, to be honest. I would love to have one.
Would you trust one? Would you have one?
I don't mean trust.
Again, going back to iRobot. Trust in the sense of this ethical sense, right? Is it gonna harm you? Is it gonna,
it's fine.
Burn you with the coffee?
I mean,
burn your house.
But right now we're talking about safety, right?
Yes. Yes.
So I think it would be fine. In this sense, I wouldn't worry much.
Okay, good. Whether it will make a good coffee, that's a different question.
But you heard that this ChatGPT, one of the LLMs, when they were trying to close it, it was
fighting back.
Fighting back, it copy itself, so it doesn't sound good.
No, it doesn't. Good. Okay, scary. Jakub.
I would say that robotics? Generally people will try to make robots more universal. So humanoid is a good example. but we should, I think, answer a question: what task we want to devote to the robots? Yes. So when I ask my friends, they mostly said about some cleaning stuff at home.
Yes, that would be my next actually idea is a Roomba, but that knows how to move chairs around or put them on a table upside down, and then maybe move some toys, my kids' toys around like this. So I don't need to do anything.
Or clean different parts of your flat, not only floor.
Windows.
Exactly.
I mean, there are robots for cleaning the windows. I have one.
But you need to have like 5-6 different robots. Yes, I would say. And the one that will cook something for you and so on.
Humanoid assistant. This is what we're talking about.
Yeah. Okay. So then I would say, but
that's the future for you. Yeah.
I mean, I'm not a big fan of having robots everywhere around me. So I would limit their functionality to certain stuff.
One robot or 5 robots, different.
In general, I think that people are still needed, and if we will devote all tasks to robots, then
that, and then we are entering into the topic of privacy as well. Safety and all of that. All robots will have sensors, cameras. Who's going to kind of tap into those and what they're going to see.
I'm not sure if this is a problem anymore because we have our phones every time.
That's true.
All day with us, and come on.
They're listening. They're listening. Yeah. After this episode, you'll get a lot of adverts from this topic on your phone. Definitely. Good. Okay. Gentlemen, thank you very much for being here. It was lovely talking to you. I have to admit, I understood a good portion of it, like I would say 85%. That's still good for me. So I appreciate it. Definitely made it a bit easier for me to understand robotics, hopefully for our listeners as well. So I appreciate your time. And if anyone has any questions, audience, they can get in touch with you probably on LinkedIn.
Sure, yeah.
And we are looking for robotics specialists, right?
Of course.
Yeah.
Yeah, so come apply for our jobs. We're good. Right?
We are the best.
We are the best. Perfect. Okay, thank you, everyone.
Thank you.
And stay curious.